What is refraction? Well, refraction is that light comes in through a film, and instead of bouncing back, ricocheting, or bouncing backwards, it goes through, but it doesn't go in a straight line like transparency would. It goes off in some direction, some angle. That's essentially it. That's refraction description in a nutshell. Okay. But one person accuses me and says, "Bill, but you haven't explained transparency very well." Oh, I thought I did. He says the following. He says, "You vaguely depicted it. You didn't actually explain refraction, transparency, opacity in the least." Well, I thought I did. Well, not refraction, because today's refraction, you got to give me time to talk about them. Opacity, I haven't talked about that either. So I thought I talked about transparency, and I thought I gave you the mechanism. So let's find out if I did or not, because this fellow accuses me and says, "You didn't talk about transparency, or you didn't explain it." I thought I did. Let's find out. He says, what's physically different about transparent versus opaque media? Well, that's a separate issue. That's a separate question. One thing is to give you a mechanism for transparency. Another one is the question you're asking is, what is the difference between this and that? How is this different than that? What's happening in each case? That's a separate issue. But to say that I haven't explained transparency, why film is transparent, I thought I did. Well, we'll cover it today anyway, so that you'll learn it well. Okay? What physically happens at the rope atom boundary to cause torsion to be redirected? Again, he's talking about refraction. That's today. Okay. The phenomena don't really follow from RH assumptions. You have to explain them. Yeah, you have to explain them, but if you explain and the other person's not listening, well, I can't do much about that, So try to listen. Okay. Maybe you missed something. Okay. Okay. Give me a second here. Okay. Here we move on, and a fellow along the same lines, but this is one of the reasons I like to cover the subject again. I thought I covered transparency, but this guy also apparently got the wrong message. He says, an object looks transparent because light waves pass through unchanged. He says the waves are not touching anything. They're just going through the material. That's what he's saying there, okay? The light wave effectively passes through unchanged. As a result, we can see straight through, almost as though the object isn't even there, okay? And the first problem we have is he uses the word wave. Well, there you have a wave. And what is a wave? Well, a wave is a bunch of vectors. There's no physical object called a wave. The flag, you can say waves. What is waving? The flag. Wave is what it does. Ocean wave, well, it's the water. So it's the water that's waving. Okay, waving is what water does. Okay, so wave is a verb. So the question is, if light is waving, or something is waving, and that's what we call light, what is it that is waving? You have to identify that thing. And you can't say a wave does this, because wave is just a bunch of vectors according to the mathematical establishment. Unless you've got something else, I don't know. But that's what we have, vectors. And vectors is a mathematical concept. It's just magnitude and direction. And what the mathematicians have done is they put them in motion. All these numbers with direction is very scary stuff. So no, there is no such thing as a wave, but even assuming we concede it, look at what this fellow is saying. He's saying that light passes through, just goes through the film and doesn't touch anything. Okay, that's what he's saying. So, imagine you're looking at a pool, water, and you can see your reflection at the bottom. And someone might say, well, now you're really seeing your reflection at the top, at the surface. Lesson. Slap, slap. Throw a nickel down 10 feet of water in a pool, swimming pool, which is crystal clear. You'll see the coin at the bottom of the pool. So don't tell me it's the reflection at the top of the pool. You can see through water all the way, your coin at the bottom, 10 feet of water, okay, or whatever. Okay, yeah, so you can't use the wave, but even if you use a wave, assuming you concede it, you grant it, you say, okay, then let's concede the wave, then what? Even so, this fellow is saying that the wave goes through all these atoms, 10 feet of water, gazillions of atoms, all the way to the bottom, and all the way to the top, I would think, right? Because if you can see your reflection all the way down at the bottom, you can see your shadow at the bottom. For sure, you can see the coin. That means at least one way you're going to get the image of the coin through gazillions of atoms or molecules of water. And the wave didn't touch anything? Just went through all of it? My God. And this is the problem, that people have these notions that they get them from experiment and from observing. And that's why observation and experimentation are not part of the scientific method. Not according to what this site does. Okay, what the mathematicians do, we don't care. We're saying science. Okay, in science, we don't use observation or experiments because you reach these irrational conclusions, which are easily debunked. And in fact, the establishment, a lot of people hold it. In fact, this notion. And here you have an example. Here's how stuff works. I showed it the other day. Okay, and these people say because air contains so few atoms, light waves run into very few of them when they shine through air. That's their explanation. So the air looks transparent. If you put enough dust in the air, the particles of dust absorb the light and the air stops being transparent. So these people think, just like this fellow here, that it's a hit and miss type of issue. You know, that perhaps when you throw your coin down 10 feet of water, crystal clear water in the pool, right? And you can see it there. You can throw your shoe if the coin is too little. Throw your shoe down there and you'll see it down there and you can see it right through the water. And so here's the shoe sending you photons through gazillions of atoms vertically, right? Lined up vertically through all these atoms of water. I guess it zigzags through all of them. Is that how it makes it all the way to the top? Is this what these people really think? I mean, they haven't figured this out. They think it's a question of, oh, if it doesn't hit, then it goes through. And I mean, is there any chance that any photon can make it through 10 feet of gazillions of molecules of water and not hit a single one? My God. So we have a problem. We have a problem because people don't understand the basics. And that's why we got to go back to transparency before we can understand, we can move on. These people, this fellow's asking a question of college question. He says, well, you haven't explained transparency. You moved on. You want to do refraction. Yeah, but see, if you don't understand the kindergarten stuff, I'm not going to move on to the college stuff. So let's make sure you understand the kindergarten stuff first. And right now, people have a big problem understanding the kindergarten stuff, okay? You can see these folks think that light goes through air. And what I'm going to argue today is light doesn't go through walls of any kind. Let's get it straight. Light does not go through any kind of wall. I don't care if the wall is made out of steel, cement, air, water, or glass, or whatever. Light does not go through any kind of wall. Light does not go through atoms. Light does not go through molecules. We got that straight? That's kindergarten stuff. Okay? Light does not go through atoms, through molecules, through walls of any kind. Okay? So we're going to show this. And until you understand transparency, I don't know if we can talk about anything else. I mean, here. And so one site says, quantity of atoms have no bearing on transparency. Absolutely. Okay? So if a film is transparent, it's got to some degree to do with thickness, with how wide it is, but primarily that's not the mechanism. It's not that if you have lots of atoms, it blocks light. Okay, and if you have few atoms, light goes through. No such monster. Light does not go through walls. Light does not go through atoms. Light does not go through molecules. Okay, if the chemical bonds in a substance have the right energy to absorb in the visible spectrum, you can see through it. Okay, so we have energy, whatever that is, it's going to be absorbed. So it absorbs the energy. So if the atom absorbs it, doesn't let it go through. But if for some reason it doesn't absorb it, or I don't know, it stimulates the electron re-emits, okay, transmits again, retransmits, okay, so that's maybe how light gets behind the atom, goes through it, okay, that's what these people are saying. So he says, if they absorb in the infrared and ultraviolet instead, such as glass, light travels through. This is what these people think, that if it's not absorbed, light travels through the film. Through the wall. Does your cat go through the wall? Well, what's different from light from your cat? I mean, try it. I mean, just throw your cat against the wall until he goes through. That's what these people are saying, that you can throw the photon against the wall and some of them will go through. Okay? So keep this in mind. This is what these people are saying, that light goes through walls. That's what these people are saying. I'm going to argue here that light does not go through walls. I don't care what the whole wall is made of. Okay? I don't care if it's a crystal. I don't care if it's silicon dioxide, water, air. It doesn't matter. Light does not go through atoms. Light does not go through walls. Okay? Let's find out here. Because this is the notion people have. They got it from intuition, from observing and doing experiments. That's why those are not important. What's important in science is that you think, that you use your brain, not that you use your eyes or hands. Okay, and this is another version of that. It says materials are transparent. Why? Because to these wavelengths of light for which there is no mechanism within the material to absorb those wavelengths. Again, all these people say more or less the same thing. And glass electrons require much more energy before they can skip from one energy band to another and back again. In other words, you have this quantum jump, and if the photon comes in and knocks that electron that's in a lower orbital, and it gives it energy, and so now the electron jumps to a higher orbital and re-emits, the sometimes some people say it just absorbs, the other one says it re-emits the signal, the energy or whatever. Consequently, photons of visible light travel through glass. These people think that light travels through walls. Okay, let's get that straight. This is what all these people say, that light travels through walls. That's what they believe. Okay, instead of being absorbed or reflected. Okay, let's find out if all this is true. Does light travel through walls? Does your cat travel through walls? Let's find out. Maybe the ghost does. I don't know. But cats? I don't think so. Okay, and so here's a fellow who tries to explain transparency. He says reflection of light occurs when the waves, what is a wave? I guess it's that moving vectors again, encounter a surface that does not absorb the energy. Ooh, energy. I guess one of these souls, these spirits called energy, of the radiation, and bounces. Here you have the energy bouncing. Jesus. Bounces the waves away from the surface. Okay, for instance, a blue hat is blue because it is absorbing light. Okay, so it absorbs light, whatever that is, whatever he meant by that. What do you mean absorbs light? What did it absorb? I mean, was it a liquid, a bunch of particles? What did it absorb? But bouncing the blue spectrum back. He bounces the spectrum. Ooh. Okay, everything we see is reflecting. Well, how about refracting? I mean, if everything is reflecting, I mean, I stand behind a glass, and reflection would be the guy on the other side, right? So he's being reflected in the mirror, in the glass, but I see him through the glass, so I think that's refracting. So everything is not reflecting. There we have reflecting and we have refracting. Okay, those are not the same thing. Okay, we call them something different. Okay? When reflecting is like when you're in a mirror, when you see yourself in a pool, like Narcissus the other day, right? But if the thing goes through and the fish sees you from underneath the water, well, your light is being refracted through that water, okay, not reflecting. Okay, we measure these waves with instruments such as photometers and spectrometers, okay? I don't know how you can measure a wave, whatever a wave is. These waves are not conceptual. Oh, okay, so they're physical objects. Let's find out. We can see them. Whoa, you can see the wave. Okay, you can see wave with tools. I don't care with what, just draw it for me. We can touch them. Well, if you touch them, you should be able to draw it. Give me a drawing of a wave and we find out what it is. Okay, what does it look like? Does it look like those vectors there, mathematical vectors? Is that what it is? Ever had a sunburn? Yeah, but so what causes the sunburn? Is it ghosts? I mean, I could say it's the spirits that do that as well, right? What's the difference between the wave, your wave, and the spirit? Looks like you're talking about spirits. It says we can measure them as 3 dimensions in our 3-dimensional environment. Waves have shape. Oh yeah, what do they look like? And what are we talking about? What is the shape? I mean, again, are we talking about these vectors? Is that what a wave is to you? I mean, if not, it'd be nice if you can point to a site that shows what your waves are. Okay, to call these waves a concept is ignorant. It's that simple. What the hell do we measure with oscilloscope? A concept? Well, you got to tell us what it is. See, you're talking about a what. And if you're going to talk about a what, you got to define what a what is. What is a what? And we're talking about an object. And this is what an object is. An object is that which has shape. Okay? And here you see there's no object in science called, or physics called a wave. And a wave is equal to a verb. That's what a wave is. Transverse wave is moving vectors. So you can't use the word wave. You got to know what an object is. And here's the object. Okay? Object is what? An object is not that which you can see or touch. An object is that which has shape. And you're saying that that thing has shape there? Well, no, because that's a concept. We're talking about concepts. We're talking about vectors, magnitude and direction, and that are moving. And so they fooled you. they sold you a whopper. They sold you a whopper that's saying that what you're staring at is a physical object when it's just what they did, the mathematicians put a number there, which is that arrow, the arrows going up and sideways. And then he started moving these arrows. So no, there is no such thing as a wave. You got to figure out what physical object mediates light. And shape is the only universal property of objects. There is no object you can imagine that doesn't have shape. Concepts don't have shape. And so if you think that's a physical object, well, think again. That's not a physical object. What you're staring at is a bunch of vectors, mathematical vectors, and those do not qualify as physical objects. Okay. Give me a second here. Get rid of these. Okay. Um, so when you look at these people, they say, okay, so we have these waves, and if they travel through a medium, and the medium for some reason doesn't absorb them, doesn't stop them, the light goes right through the medium and reaches your eye. And so here we have an example. We have these waves of light coming from maybe a star or the galaxy. And what these people are saying is that when these waves approach the Earth, the air in our that covers our Earth, the particles that don't block the waves, those waves will go through and reach your eye. That's what these people are saying. Okay, and that's strange because the official version is that the reason you see the sky blue or light blue is that there's refraction going on, not that you're receiving the wave directly from the star or from wherever out there in space. Okay, so there's something wrong here. So there's a contradiction in what these people are saying. They're saying light that doesn't get caught comes to your eye, and turns out the light always is blue. And it's blue, why? Because they say the air scatters the light and only allows that frequency that is bluish to reach your eye. That's a different story than saying that light goes through air and doesn't get caught by any molecule, any atom out there. Those are two different mechanisms. So either light goes straight to your eye through air, through all the molecules, through the wall of air, of this wall of gas, or it doesn't. It gets trapped somehow and it only re-emits to your eye whatever frequency gives you that blue color. It's one of the two. It can't be both. Okay. Okay, here are the possibilities. Okay. Let's look at the possibilities here. Either a photon goes through empty space of the atom, right? Remember, Mr. Rutherford says an atom is mostly empty space. And so people have this idea that a photon can go through that empty space part of the atom. Or a photon strikes an electron bead, in which case there's two versions there. One is that it absorbs this wave or this energy, whatever they call it, and then it doesn't go through. And another one is that if the photon, the energy hits this electron bead, the electron bead then re-emits that same frequency or energy or whatever. And then another version is that the photon can travel between two atoms, which is what all these people are saying, that if it doesn't get caught in any way, shape, or form, then it reaches your eye. Okay. The other one that nobody considers is the fact that Rutherford showed that certain type of particles hit the proton, and that's why they bounce back. Why doesn't the photon strike the proton and bounce back? Or does it? I mean, nobody talks about the photon hitting the proton. Everybody just talks about the photon hitting the electron. Okay? And then there's another possibility here, and that's the photon fails to hit any atom. Okay? And the question is that possible? I mean, if you look at the one on top, it went through two atoms because there were only two atoms. What if you have a bunch of atoms? You have layers upon layers, like I said before, pool of water, 10 feet of water. You get gazillions of atoms there. And you're saying that photon is not going to strike any atom when it goes through there? And this is the same version here, but with a wave. Okay, so if you're a wave guy, well, there you have the waves. The question is, what is a wave? But even if we concede the wave, we have the same questions. Does a photon go through, like between two atoms? Does it go through the empty part of the atom, or does it get relayed once it strikes the electron? Okay, those are the main probabilities, the main possibilities. Okay, here we have the situation. We have the fellow looking through a window. And what we have is that the sun is, according to these people, is sending the waves to his eyes as if air wasn't there. Okay? So transparent, according to these, and the glass as well, by the way. So it's like the glass and the air are inexistent as far as they're concerned. It's like the sun just sends the waves to his eye directly. It's those waves or photons that do not get caught by the silicon dioxide or the oxygen in the room, the air in the room, right? That reaches eyes. Okay, that's their theory. Here we put a little bit of air. Okay, let's put some air in there. And so what these people are saying that wave goes through all those molecules that are floating around, not to mention the ones that make up the glass. But here we're only having the air molecules. And these folks are saying that the waves of light go through all these molecules. And I didn't draw them all. I mean, there's gazillions more than what you see there. and it doesn't. And those waves of light or those photons never hit a single one of these. Just go through them. This is what they're saying. Okay, so keep all this in mind. Okay, what do we propose instead? Well, we propose that this is the way you're supposed to look at this, whether you're talking about glass or air. What you have is relaying of the signal through from atom to atom through the ropes that interconnect them. So you're talking about something traveling at the speed of light. So you see the window instantaneously, essentially. And does that mean that the image from the window is coming to your eye through nothing? No, it's being relayed from atom to atom through all the wall of air that you have between you and the window. The signal is going from molecule to molecule, from atom to atom, from the window to your eye. So you have this interference there. You have a relay race from atom to atom. That's our argument. Okay? So no, nothing goes through walls. It doesn't matter if you put water, the wall is made of water or of, of cement. Nothing goes through walls. Okay? So we have to explain these mechanisms. And the mechanism is that light does not go through atoms. What it does is the rope ends in an atom, stimulates that atom, doing its quantum jump. All this at the velocity of light. We're talking about gazillions of gazillions of gazillions of atoms, re-emitting that signal to the next atom, which re-emits it to the next one, all at the speed of light. Okay, because it's so you get the signal directly from the window, assuming that's what you're staring at. You get it from the window directly to your eye at the speed of light through this relay race going from atom to atom. It's all like if. Then it is as if the air wasn't there, because they're all relaying that signal. Why? Because it has the frequency that it can be sent as if the light wasn't there. Okay, so it blocks some light, like in the case of silicon dioxide window, it would block, for example, ultraviolet light. That would not reach you. But what continues is the regular light that you receive from the window. Okay, so that's the atom that's stimulating that signal. That if your window is brown, that's the atom that's the frequency that's being sent to your eye. All the others are absorbed. And so again, it's a relay race, according to us. Okay, and we have a bigger problem, which is the quantum atom, and that's this thing that they have, the planetary atom. They have different orbitals, and there you see the electron bead, blue, going from a lower orbital to a higher orbital, or you could say from a lower energy level to a higher energy level, and vice versa. So what's the problem with this? Well, even if we concede this, we have a problem here because we can't understand why that blue bead doesn't leave spontaneously, doesn't leave the atom or fall to the center of the atom. We don't understand that just by looking at this. That's never been explained, and quantum cannot explain that. They just use this model, but they never explain it. They can't justify it. But what happens if we start throwing some photons at it? Okay, and here we throw some photons. Okay, these red little balls that are coming in there. And remember that when the atom falls to a lower energy level, it emits, and when it rises, it absorbs. Okay, so you got to keep that in mind. And the question here is, assuming we concede this atom, right, this model of the atom, the question is, you have this little bead, this little red bead, and it just happens to hit the little blue bead, and both of these are zero-dimensional. They don't have any diameter or radius. They have no size. But even if you give them a little bit of size, I mean, what is the possibility that the photon will just happen to hit that electron bead and be absorbed? What happens to all the other beads that come? I mean, if you're talking about gazillions of photons coming to that atom, well, one of them or a few of them might knock that electron to a higher level or whatever. But what happens to all the others? Do they just go through? So again, we're talking about going through the atom, no matter how you look at this. Okay, so keep that in mind. They don't have a solution to all these because they never illustrated what they're talking about. Okay? They don't care to because they don't understand it themselves. Okay, so here we have a wall, and we'll call this glass. Okay, so these are the atoms. Okay, now we're going to shoot some photons at it. Okay, let's shoot some photons. There we go. Okay, we have the first layer, then we have a second layer and a third layer. Okay, I guess the more material you put in there, the more that bounce out, I guess, or the fewer that go through. But this is the notion that they have. All these photons are just going through the film, whatever that film is. It could be water, it could be air, it could be silicon dioxide, glass. Okay, so the photons are going through. Okay, now some of them strike the surface, okay, and just bounce back, okay, or go through. Then you have reflection. Here you have reflection. Some hit and bounce out, others go through. Okay, so it's a pretty big mess there because you have all these photons. Some go through it because the film could be transparent. Some refract, means that they take a different angle once they hit the film, and others bounce back outwards. How does Mother Nature do all these things? I mean, some bounce out, some go through, but turn the corner, go at an angle. Okay, how does Mother Nature do this thing? Okay, and so here we see what we're proposing. If I can find it here. In a second here, there we go. This is our model of that same thing, a little better organized. What you have is light coming in, again, from the left, and it goes to this film, that's there, and some of them are transparent, some go straight, some are at an angle, which means they're being refracted, okay? So not all of them go straight, not all, and again, you get the reflection along the same rope. So you have reflection, refraction, and transmission, or you can say, I call it relay, but it's transparency, okay? So you have it all there, okay? You can have light just go straight, just simply stimulating the film and going out the other end. You can have it go at an angle, which is refraction, and you can have reflection along the same line in which that film came, the light came. Okay, so this is our model compared to, again, here's their model, little balls. You figure it out. You figure out which one is the more palatable to you. Okay. Here's what I talked about earlier, that you can see the bottom of a pool. Okay. So if you want to run the test, people who like to do experiments, here you have a chance to do your experiment. Just throw a nickel or a shoe or whatever to the bottom of the pool, see if you can see it. If you can see it, that light coming from the bottom of the pool is coming through gazillions of atoms or molecules of water. That's what you got to explain. And if you're going to tell me that that photon ball or that wave or whatever you're going to use as a medium zigzagged or somehow made it through all those atoms, well, I don't know. You got a problem there. Because, and again, you see there the guy on the right, he's looking through a little bit of cardboard, and he can't see through it. He can't see, in other words, it's opaque. Whereas water, a lot thicker, a lot more atoms, and you can see through it. So this is what you got to explain. This is what's on your table if you want to explain reflection, refraction, and transparency. Okay, give me a second here. We did an experiment with my son. I showed this sometime in the past, and that's we put a mirror in a trash can, filled it up with water, and you can see all the way to the bottom. Okay, so this is more or less like the shoe that I was talking about. You can put your shoe at the bottom of the water. Here we filled the tank up with water, and we can see the mirror all along. In fact, we filled it up, and you can see the mirror. The light from the mirror comes up, and we can see ourselves down there. Okay, so hopefully we did not see the reflection at the surface. Okay, that's what we were trying to show there. Okay, let's move on here. Here are my main points. Okay, for those who question whether I explained transparency, I think I did. I'm explaining that light comes in, how? Through a rope. There's a torsion. Stimulates the atom, okay? And that one stimulates the other atom, and it comes out the other end. That's transparency for you. What part of that mechanism did you not understand? Okay? He said, I didn't explain it. Yeah, that is the explanation. Sorry, it doesn't get any better than that. That's kindergarten stuff. Now, if he says, why is this one opaque and why is that one transparent, that's a separate issue. But he can't say that I have not explained transparency. Transparency means torsion being relayed from one atom to the other behind, in the opposite direction from where, or in the same direction, sorry, from where the light came. Okay? That's transparency. And I thought I explained it. He says I didn't. Well, he didn't understand it. He's still struggling with the kindergarten stuff. Anyways, here are the main points. QM, quantum mechanics, does not have a physical interpretation. In other words, an explanation for reflection. Or refraction for that matter. Science is equal to explanations. If you don't explain, you're not a scientist. Physics is physical interpretations. Okay? So quantum mechanics is not a part of physics. Why? Because they cannot explain. They cannot explain the mechanism. That's essentially it. They don't have a physical interpretation for reflection, for refraction, for transparency, opaque, for none of that. They can't explain it. They just say transparency means that some of the light got through because it wasn't caught. Out of gazillions of atoms, none of them caught it. That's pretty good shooting there, you know. Okay, and then so QM is not equal to science, and we must first debunk quantum mechanics before we can move on to something to consider an alternative, because right now that's what's standing in the way, quantum mechanics. Okay? We have to establish by debunking, I mean, that it's irrational, showing that it's irrational. Here's what they talk about when they talk about refraction and essentially reflection, opaque, any of those. The establishment only calculates angles. Okay, every time they say, well, what is reflection? What is refraction? They immediately start talking about angles. I don't care about your stupid angles. I don't want to hear about your angles. I want to know the mechanism, not the angles. They measure the angle, say, I measure the angle, give me my Nobel. Who cares your angle? That's the question I was saying, like, I measured the table, it measures 1 meter, give me my Nobel. Is that science? Just measuring and saying this is the angle? Those are things that don't require any mental capacity. The mental capacity is figuring out how the magician did the trick. That's where you got to break your head. Quantum mechanics, no rational physical interpretation for anything. They have no explanations. And they can't rationalize it with waves. They can't rationalize any of those phenomena with waves. They cannot rationalize it with discrete beads, the so-called quantum, okay, the unit of quantum mechanics. And don't take it from me. Here's Mr. Feynman. He tells you, will you understand what I'm going to tell you, you think? No, it says, you think I'm going to explain it to you so you can understand it? No, you're not going to be able to understand it. You see, my physics students don't understand it either. That is because I don't understand it. Nobody does. While I am describing to you how nature works, you won't understand why nature works that way. In other words, the mechanism is what he cannot explain. But you see, nobody understands that. I can't explain why nature behaves in this peculiar way. Why? Because he cannot explain a mechanism. And why can't he explain the mechanism? Because he's trying to simulate it with waves and particles. Anyone using waves and particles should be kicked out of science, because it's been shown, at least in the last 400 years, that neither waves nor particles can give you a rational physical interpretation of how Mother Nature does her stuff. This is where the problem is. Got to get rid of, got to raise the board and start all over and say, okay, well, where did we go wrong? We went wrong with a wave, we went wrong with a particle. That's what we have to erase. We can't continue using it, waves and particles. So here's my conclusions, okay? Light is not equal to a transverse wave, okay? There is no such thing as a wave. Those are moving vectors, scary stuff. Light is not equal to a stream of discrete particles, right? Discrete beads, corpuscles, grains of sand, whatever you want to call them. Quantum mechanics has no rational explanation for what? Transparency, reflection, refraction, opaqueness. None of them. They cannot explain any of those. They say that's not science, that's philosophy. Okay, reflection is not equal to bouncing balls. Opaque is not equal to dead photon balls. Not that the photon ball comes and dies there. Okay, so that's not opaque. Not the mechanism of opaqueness. Okay. Transparent didn't strike anything. Is that what transparent means? That it just didn't strike anything, wasn't absorbed, so it kept going? You received the light directly from the sun because none of the air molecules stopped that ray of sun. You received it directly in your eye, huh? Is that what it is? Yeah, so light goes through walls, right? Okay, refraction is not equal to passing through, okay? In other words, for refraction, you have to have that angle. You have to have something that deviates it, okay? Now with ropes, you can explain at least that, you have that straightness going in and you have the straightness at an angle. How do you do that with particles? How did the particle suddenly, swerve at such a sharp angle and go straight again? How do you do that with particles? How do you do it with waves? I mean, why would the wave go, let's say 30 degrees from the normal? So here's your wave coming in straight to the mirror, or to the glass, let's say the glass, and suddenly it goes at an angle to the side. Could be a prism, could be anything there, right? So it goes to the side. How do you do that with waves? How do you do that with particles? But with a rope, if every atom is connected, you connect the dots, then at least you can conceptualize that, yeah, the rope gives a signal to that first atom, which sends it through an angle to the other atom, okay? And yeah, you're going to ask me, well, why does it go in that direction? Well, that's a subject matter for another day. Right now, we're still struggling with the kindergarten stuff. Right now, we're trying to understand the mechanism. People think that light goes through walls. That's the problem. So we need to settle this kindergarten stuff first. Okay, reflection, refraction, transparent equals to relay. Everything's done through relay. You can only explain that. As far as I'm concerned, the only way you can explain it is if all atoms in the universe are interconnected, physically interconnected. In this case, by a torquing rope, or torquing ropes, plural. Wave and particle, they have to fly, they have to strike, and they have to resend in the best cases. In the case of transmission, transparency, it doesn't hit anything. And you explain that one to me. I don't know how a photon can do all that magic trick. Rope torques in situ bidirectionally, very easy to understand. Light works as a chain reaction. Remember, like fireworks. You hit that first one, that one sends it in different directions. Those also send it in different directions and so on. So light, and remember, you're talking about gazillions of atoms, gazillions of ropes, photons. Okay, so you're talking about a world in which you're talking about something so small you cannot even imagine it. That's how small this thing is. And you're talking about millions and millions and millions and millions of atoms and ropes. So it's not, we simulated with one rope just to show you the mechanism, but you got to think of this as something so small and so numerous that it's unimaginable. Okay, that's important. Okay, to put it in that context. Okay, reflection, refraction, transparent, always work straight. Light always travels straight. The only way you can get it to travel straight, guarantee that it travels straight, is if you have a mediator that is taut, that is stretched out taut. Okay, it's tight. Tightrope walker can walk on it. Atom Man, just balancing himself. One-way waves, particles can't do straight. That's the problem. You cannot explain straightness with particles, especially if everything in the universe is moving, especially if you introduce or factor warp space. All bets are off then. Not only are we moving, but we have warp space, and they're talking about what? That particles travel straight or rectilinearly? Impossible. Especially through warp space again, and rope extends straight. It doesn't travel straight. It just extends straight. Okay, and for our world, we can say that the rope is straight. Obviously, it's an undulated, entity. Okay, it looks like this. You cannot say that's straight. You can only say that maybe the axis that runs along a taut rope is completely straight. Yeah, but for all practical purposes, for what we're talking about, the invisible, skinny, thin world of Mother Nature, a rope is straight. For our macro world, you can say that's the straightest thing you can imagine.